Hi everybody, this is Distributed Systems. This lecture is about the cloud and the Internet of Things. As ever, I'm not actually Bjorn Franke, I'm Hugh Leather. Okay, so today we are going to talk about cloud computing and how it relates to distributed computing. We'll go through some examples and then talk about things like software as a service, platform as a service, and infrastructure as a service. There are a whole bunch of those things ending in AAS, as a service. These are just three of the common ones. We'll talk about the Internet of Things and various bits and pieces about it, like the applications, architecture, and so forth, and some of the issues involved in scalability, security, and privacy. So what is distributed computing? Well, as we've seen before, the idea is that you want to do some computation and everything should appear like a single system. The idea is that you should be able to write your code as if you are just running on some enormous distributed machine. So you have a bunch of nodes, computing nodes, which are connected to each other, and that's the substrate on which your computation works. Some examples of distributed computing systems. Well, the World Wide Web is one. There are machines all over the place. You access them by various addresses and you have a communication protocol that goes between them. Pretty much every major website is backed by a large distributed computing system. Facebook, for example, all their data centers are all distributed. Hadoop's distributed file system is a common example, which can scale to tens of thousands of machines, maybe more, to hold truly large amounts of data and be able to serve them up with low latency. Automatic teller machines, or when you go to a bank machine, each of those machines is of course in a different physical location connected by the network. So that is a distributed computing system. And cloud network systems, which are a sort of specialized form of distributed computing system, which we'll talk about in a little bit. We've got Google bots, the things that go around and spider through your websites, trying to find out what's going on there. Various Google services and pretty much every web service that you see is a distributed computing system. In the master-slave architecture, a number of clients communicate to a master who gets slaves to do their work for them, and that's how that works. The benefits of distributed computing are that instead of having a scale-up massive single machine, you can buy lots and lots of cheaper machines and save yourself a lot of money. They are easier to grow if your computation can be scaled out in that way, allowing you to have more computational power as you bolt on more computers to the system. And because you can incrementally grow the number of computers involved, it means that you can start small and grow later. Here are some examples of cloud computing. YouTube is a good example of cloud computing. The videos that are stored on YouTube constitute a vast amount of storage. So there are millions of machines connected to hard drives and solid state drives that serve up the YouTube videos. Picasa and Flickr are probably a bit old now, but Instagram maybe has millions and billions of digital photographs and short video snippets, and these are all hosted in the cloud. Google Docs is another example of this, where your Word documents, spreadsheets, and so forth are put onto the cloud for these things. So what is the cloud? It is essentially the idea that things you would locally you previously have locally stored on your machine, you now can store them on a distributed system somewhere out in the net and not have to do it locally anymore. And not just store them, but also interact with them. So the ways that different companies provide their services to users can be different. Uh, there are three main ones, but there are lots and lots of other variations of these things. The main ones are software as a service, platform as a service, and infrastructure as a service. And essentially, the idea is that instead of building these things out yourself, you use somebody else's servers to host, process, and store your data. And these three different formulations of this describe how much you have to do yourself in order to make use of those resources. So we'll talk through each one of these as we come. So the first, let's look at software as a service. The idea here is that somebody else provides a complete piece of software that you access and you don't have to do any programming or any setup beyond your employees logging onto it and so forth. So a good example of this is Google Docs. So if you are a company wanting to use software as a service, then you can sign up. I think Google Docs has a commercial version of their stuff as well. But even if you don't, you can just log on to Google Docs and start using their word processing, spreadsheets, etc., instead of having to download Microsoft Office onto your machine. And you will notice, of course, these days that Microsoft Office has a cloud provided version as well. There are a couple of typical delivery models for software as a service. The first is that the provider gives some already available software and enables customers to use that directly on the web. So they might not even write the software themselves, or maybe it's a slightly modified version of their non-web hosted software. So I guess the Microsoft Office programs fit into that kind of model. And then there is software on demand, where the providers give customers access to some copy of an application that's been created specifically for this form of distribution. And this Google Docs is probably a better example of that. Why do people do this kind of thing? Well, it means that they don't have to administer it themselves. They don't have to do updates and patches and make sure that everybody's Microsoft Office local versions are up to date. Make sure that everybody's using the same thing. And when everybody's doing that, you can also collaborate. People tend to build in better features than you have on the single user systems. You can have multiple users editing a document on Google Docs, but you can't do that quite so easily when you have only a local hosted word browser or something like that. Similarly, even for LaTeX these days, there are cloud versions of LaTeX like Overleaf, where it is a lot easier to collaborate using that than often it is easier to collaborate using that rather than using source control as a backend for collaboration and having your own LaTeX distribution on your device. So that was software as a service. Platform as a service is a slightly different system. So here, rather than delivering complete applications that users can use directly, the provider gives you an operating system and various tools, tooling and libraries, etc., on top of which customers build their own software. So Microsoft Azure is like this, AWS, Amazon Web Services has systems like this. And the infrastructure is provided. You have all of these, as I say, the operating system, etc. Users now don't have to worry about having their own hardware. They don't have to keep their operating systems up to date to run new applications. And examples of these kind of things are, you might have somebody who gives you platform as a service, and they say, we will give you Java virtual machines into which you can run your code, probably with some restrictions on what kind of things you can access from it. This means that then you can, if you know how to write Java, you can develop on your local machines and upload up to some other system like Google's App Engine and so forth, where you can then, your programs are then hosted on their machines. The last of the ones that we're going to talk about, though as I say there are many more, is infrastructure as a service. The idea here is that the provider, like Amazon or Microsoft, they don't require you to use a particular operating system or anything like that. They give you virtual machines that will be hosted on their servers, and you choose your own system, your own operating system. Everything is provided by you, but you don't have to worry about scaling up the resources because you can always get more machines off them. You don't have to keep your hardware up to date. Your VMs run only when they need to, so it's hopefully much cheaper for you. So that is essentially what infrastructure as a service is, where they basically just give you the hardware and a way to install your own virtual machines to work on those. So what are the benefits of cloud computing? We've talked about several of these. Scale and cost. It can often be cheaper to rent machines by the minute or by the hour when you don't need 10,000 machines in the middle of the night. Don't pay for them. Use them at hot times of day on somebody else's system. And so that's scale and cost. Other benefits are that when things change, then the servers, the providers usually give you a way to roll out your changes onto all of the devices, all of the servers that you have taken account of. You don't have to upgrade your systems, so you will probably be using recent computers rather than your old crappy ones that you had down in your basement before. Amazon's web server, Amazon's EC2 service has some quite nice machines available to you, and because these companies have different offerings, then you can change what you are looking at and select different services depending on what it is that you want. The downsides are, well, once you have built something to use Amazon systems, it's very difficult sometimes to move to somebody else's system, which means that you might be locked into them, and that comes with its own risks. You are also placing a great deal of trust in that provider's security systems. You hope that they do a reasonable job of not letting your data get out to somebody else. You don't control what's going on here, and so you can't change things that you might otherwise want to do. And reliability is also something that is up to somebody else, which means that when machines go down, hopefully they get put back up and your systems are moved somewhere else, but you don't have any control over these things. There are now, by the way, there are companies like Pure Storage who actually are providing cloud computing, or intend to provide complete cloud computing systems that other companies can buy ready-made cloud computing boxes that they can install internally to give them the benefits of the cloud whilst actually maintaining control over it and having some lower cost under certain circumstances. So, what are the goals of cloud computing as opposed to distributed computing? Well, one thing to remember is that cloud computing is just a specialized form of distributed computing. So, in a very real sense, they often share similar goals. Distributed computing makes it easy to collaborate over particular resources, connecting users and those resources. And it should make it easy to administrate the systems and resources that you have, and to make systems which scale to large number of processes and users across geographic regions. Cloud computing is more about the delivery of the services and applications that people need without having to have software on their machines to do that, right? So it's using the web browser often to be able to access things that previously they would have done by having dedicated software on their machines. And it shares the goals of distributed computing of wanting scalability and security, making monitoring and management easy, and that's basically the differences between the two. There are various different types of distributed computing. Distributed information systems share information across different servers to enable high availability and lower latency, and typically use communication models like remote method invocation and remote procedure call. Distributed pervasive systems have a large number of embedded devices like ECG monitors, wireless cameras, PDAs, sensors, mobile systems, and so forth. One of the crucial things for people to take account of when they are designing these systems is that these devices disappear and come online much more frequently than they do in more reliable distributed computing systems. And then you have general distributed computing systems as sort of the more traditional things where you have a number of servers communicating through message passing to keep track of their actions. There are different types of cloud computing. Private clouds essentially replicate the same kind of public cloud systems that you are used to, but they remain internal to an organization. The IT organization within a company will host applications for different parts of the company, and that company then has complete control over the data, and assuming that their security is managed, they don't have to worry about security issues. They also get better latencies often because the devices are internal to them. The expense they have to pay is that they have to actually buy the hardware, and depending on how they have built this, they may not be able to overflow into public cloud systems. Then you have these public cloud systems, the things that you will probably all have used, Gmail, Google Docs, and so forth. These are the things provided by some service provider and made available to everybody in the world. The downside is that you have no control or even understanding of what's going on underneath. You have to put your entire trust in the company who run it. Community clouds are essentially like the private cloud systems, except that multiple different organizations own parts of them, or share the resources that are put in there. And hybrid clouds are some combination of these. This is quite common to have when you have private cloud systems whose capacity is limited, and if they are overloaded for any reason, then they may move to a community or to a private cloud temporarily to handle the excess workload. The different characteristics of distributed and cloud computing are that distributed computing, as I've previously said, is a superset of cloud computing, and the tasks are distributed among multiple computers. We are often looking at computations to be done at the same time using remote procedure call. And cloud computing is a sort of specialized version of that, where it's more often about providing access to a shared pool of resources and to storage, etc., and applications. Okay, so now we change from looking at cloud computing to the Internet of Things. So, the Internet of Things is an idea about having internet connected physical objects. So, the type of examples that you might see are internet enabled light bulbs, light switches, um, heating systems, you control your central heating from work. Uh, Toasters, good heavens, why anybody wants an internet enabled toaster, I do not know. Cars that are enabled with the internet control and so forth, and all of these things. Okay, and each object needs an IP address and some way to interact with it. If you are doing these things for yourself personally, then you probably only have a small number of them to deal with. But large factories, for example, may have sensors all over the place, battery operated perhaps, maybe some of them plugged in, and they need to be able to aggregate data from them. So they pose some challenges in terms of how one connects to these devices and extracts information from them. Applications for the Internet of Things includes creating behavioral statistics of how people use media, etc. Monitoring the environment, everything from air quality to earthquake early warning systems. Monitoring the infrastructure that we have, so for example, knowing whether your bridge is likely to fail, controlling railway tracks, wind farms, etc. Manufacturing uses this kind of stuff a lot to monitor their equipment, to do things like finding where things are in warehouses so that they can get deliveries to happen faster. For energy management, so by having switches and power outlets, bulbs, televisions, etc., internet connected and being able to be turned on and off, then you can save energy. You will notice that lights often have, in large office buildings, often have both motion control and it turns out sometimes they have the ability for central turn off to keep their energy use low. Medical and healthcare systems, where people will have devices on patients so that they can go home and to make measurements of them for safety. Building and home automation is probably where most people will have seen the Internet of Things firsthand. Transportation, there will be multiple devices inside fancy cars. My car doesn't have any of those, but there you go. So, of course, once you have this idea of having billions of devices everywhere, you need some way to address each one and to talk to them and receive information from them. In 1999, I think, there was the Auto ID Centre, which was started by, I think, a grant from Procter & Gamble over at MIT. And the idea was that they were going to use radio frequency ID tags and a particular code associated with each product, an electronic product code, EPC, and use these in combination to address each of these objects. This died away eventually, and people are now, the new idea is to use IP addresses or universal resource locators, URLs, URIs. IP version 4 addresses only had 32 bits, which meant you could only get about 4 billion devices referenced here, which, given that today we have more devices than we have humans, and there are more than 4 billion humans, was not going to scale very well. So IPv6 is 128 bits, which gives you something like 340 billion addresses or something like that. which should be enough to keep us happy with addresses for some time. So here is the type of architecture that you might see in an Internet of Things environment. You would have your application layer up at the top, where you would have your environmental monitoring, power interfaces, whatever it might be. Middle layer to enable standard kinds of things to be done, like managing users, authentication, billing, etc., whatever there might be. And then a lower level where you have cloud computing and platform stuff. The networking layer beneath, again, general networking, but this time probably allowing for mobile networking rather than just wired networking or Wi-Fi. And then you have different levels to enable you to, different layers below to enable you to successfully gather data from multiple sensors, knowing what to do with them. Low-level hardware control for your sensors and RFIDs, and ways to be able to aggregate all of the things that come through. Kind of example that you might see would be an internet-enabled car. Again, sounds horrific to me, but there you go. You might, in Intel's view of the thing, you would have the roads, or embedded in the roads would be data pipes. Then your car would be able to communicate with other cars to be able to manage crashing, and I've heard people talk about sharing music between cars, which seems utterly pointless, but there we go. And for traffic signals to be smart traffic signals to give you information and to receive information from your car and so forth. The sort of underlying idea of why people want Internet of Things is to have intelligent devices and sensors everywhere, extracting and using data, that sensor data and things like that. It should have an architecture which is shared between multiple devices, easy to use, and propagate up into whatever servers you want to have involved. The number of objects and the types of objects changes all the time. You have new things arriving and disappearing. Somebody will invent some new internet connected device, like, I don't know, maybe you'll have internet enabled weights for people who really like going to the gym, and then you'll have to deal with those. Whereas in previous systems you have much more control over what's going on and which devices come and join your network. Here you have less control, and the scale can go up dramatically. ARM and companies like that are expecting there to be many, many billions of devices connected, and those will generate daily or hourly or per minute billions of different events that are all parallel and simultaneous, that need to be aggregated, processed and handled, requiring large amounts of bandwidth somewhere, either out at the edge of the network or in some server farms somewhere. You also need to work out where each of these devices is, so that, for example, you have identified which light bulb you are particularly talking about, which is fine for the home automation kind of area, because users will be prepared to describe the location of things. But if you are a factory putting tens of thousands of sensors around, then this can be quite difficult. You also have to deal with everything as a service. The idea here is that more than just providing software as a service, platform or infrastructure as a service, every device can be offered up as a service to other people to do various things. The number of devices involved in IoT is going up exponentially. There are about 7.5 billion people on the planet at the moment, and it is estimated that there are something like 50 billion connected devices. That was more, the number of devices grew to be more than the number of people quite a few years ago. And hence, naming and understanding what each of these devices are becomes difficult, and the amount of data that can potentially be streamed back from these things is also something that needs to be dealt with. Security for IoT devices is an issue that is difficult to deal with. If you can physically access a device and nobody is around to see you do it, then you can often gain access to critical functionality. On top of that, these IoT devices, small sensors, etc., have small amounts of energy and tiny processors and memory, and therefore can't implement complicated security schemes either in terms of the amount of processing power they have on board, or more often in terms of the amount of time it might spend sending information back and forth to implement some security schemes. They are not very resilient to authentication attacks, proxy attacks, man-in-the-middle, and so forth. So this means that it is quite often the case where you will see existing IoT systems which have very little security involved in them at all. So the last of Bjorn's slides just makes some notes about the privacy of IoT devices. There are a bunch of ethical and legislative issues to deal with for IoT devices. How you manage your smart home monitoring equipment and the security that you have there is part of a legislative and ethical issues. It is much easier for a person to get involved in IoT without being entirely aware that they are doing it. When you buy a car these days, you might find that it has IoT devices embedded in it, if you buy an expensive car perhaps, and you may not be aware that that has happened. Similarly, people may be unaware of the potential consequences of having everything from energy meters in their houses, which can potentially tell people whether they are there and what kind of things that they have been up to. And the public is generally unaware of how long the data is stored for or to what use it is put. And we don't have enough solutions at the moment to be able to keep people secure and safe from potential attack. Okay, so that's the end of the things about Internet of Things.